Starting in on chapter 6, which is all about thermochemistry and the energy transfer in chemical reactions. This picture up here is the Heisenberg exploding in 1937, New Jersey. It's a ship filled with hydrogen gas. Hydrogen gas is a very flammable gas, and it lets off tons of energy when hydrogen gas blows up, explodes, is ignited. Sure. This reaction down here is the formation of water reaction. We're going to talk quite a bit in this chapter about enthalpy, and enthalpy gets the symbol H. The enthalpy of formation of water is this equation as given. You make 1 mole of the product, and you combine the elements in their standard state in the simplest ratio possible to make 1 mole of product. That's the enthalpy of formation of water reaction. This particular reaction lets off energy as a byproduct of the reaction as well. Energy. Some reactions require energy to be input to occur, and some reactions, energy is a product. Energy is released as the reaction happens. And we're going to spend quite a bit of time determining whether energy is put into or comes out of certain reactions in this chapter. First, we got to talk about what energy is. Energy is the capacity to do work. Maybe you've heard that in physics before, maybe not. There are lots of types of energy. Thermal energy is associated with a random motion of molecules. We're going to talk quite a bit about thermal energy. Chemical energy is another one that we will talk about in this class, not necessarily this chapter, but energy stored within substances. Electrical and potential, you've probably heard of those before, and kinetic energy is actually something we talked about last week with gases. Energy has the unit of joules. Joules is a combined unit, which is kilograms times meter squared per second squared. Instead of writing all that, kilograms times meter squared per second squared, we give it the unit joules. A heartbeat is 1 joule of energy. You will also hear calories as a unit of energy. That's the conversion factor between joules and calorie. Note this is a little c calorie. If you look on the back of your Snickers bar, you will see something called calories, but we call those big C calories because 1 big C calorie is 1,000 little c calories. So when you see that your Snickers bar or something is 280 calories, it's actually 280,000 little c calories. It takes a lot of heartbeats to burn off 1 Snicker. All right, so thermochemistry specifically is the study of heat change in chemical reactions. We're going to need to define what heat is, but that's still a couple of slides from now. So heat change. You need to know what can come in and what can go out in a system. We're going to have to define our system and our surroundings and things like that in this chapter a bit. If you have these systems, these are 3 different types of systems, but the system is the bottle and things going on in that bottle. The surroundings is everywhere that's not the bottle. An open system can have heat transfer into and out of the system, and it can have mass transfer into and out of the system. It can exchange both. A closed system can have heat transfer in and out, but the mass cannot transfer in or out. And an isolated system cannot have either energy or mass transfer. So there are a few laws of thermodynamics. We'll talk about the first law a lot this semester, the second law a lot next semester, but the first law of thermodynamics says energy is conserved. Cannot be created or destroyed, energy is conserved. If you have a system and energy goes into it, the energy of the system must increase. That actually, not where I'm going here, but that actually also means the energy of the surroundings must decrease if the energy of the system increases in order to conserve. If energy is taken out, the energy of the system must decrease. So we're going to talk about 2 main ways that energy can transfer, and heat is one that I've talked about quite a bit already. It's the one we'll talk about the most. but work is another way. A system can do work, or work can be done on a system. Heat can enter or heat can exit a system. A positive sign means coming into the system. A plus means coming into. A negative means exiting. So positive energy transfer means entering the system. Negative means energy exiting the system. And that's a very important distinction to make as early as possible in your brain. Keep it straight. So heat is a transfer of thermal energy. That's where we're talking about heat transfer most. That's what we're talking about most in this chapter, heat transfer in chemical reactions. Temperature is how hot an object is, and thermal energy and temperature are not the same thing, actually. So this coffee cup is at 90 degrees Celsius. This bathtub is at 40 degrees Celsius. When they both cool down to room temperature, which will happen eventually for both of them, heat will leave the system. You can talk about how much heat, this is heat, you can talk about how much heat left the system, and 135 kilojoules left the coffee cup, but 3,000 kilojoules left the bathtub. This coffee cup was hotter, yet it lost less energy than this bathtub. Why? The temperatures were different, but the amount of substance that you had was also different. So heat transfer depends a lot on the amount of substance that you have. This coffee cup had a greater joules per gram loss because the mass of water, mass of coffee in the cup versus mass of water in bathtub is less. But the bathtub had a greater energy loss overall. Yeah? Okay. So we're talking about heat transfer into and out of a system. And when we call something exothermic, that means heat is exiting the system. Exo means exit. Heat is exiting the system. And anything that has a Q that is negative, a negative sign means exothermic, a negative sign means exiting the system. This reaction that I showed you from the beginning, this is actually multiplied by 2 throughout, but this is an exothermic reaction. Energy is a product. This next reaction, this is liquid water becoming solid. That's freezing. Liquid water becoming ice. In order for liquid water to become ice, energy must exit the system. Liquid water is at a higher energy shelf. We're going to talk about enthalpy plots quite a bit, but liquid water is at a higher energy shelf than solid water. Oops. Energy must exit to go from a higher shelf to a lower shelf. Exothermic. Endothermic is the opposite. It's a positive delta H. Endo means into. Yes, I realize I spelled that wrong, but I did it on purpose because it helps me remember it. Endo means into, and that has a positive sign. Q has a positive sign. So here are two endothermic reactions. Energy is added to this mercury oxide to become liquid mercury and oxygen gas. In the same way, energy must be added to ice in order to melt it to become liquid water. This one, students feel very comfortable with, knowing that you have to put energy in to melt ice. They feel much less comfortable with the fact that energy must come out in order to freeze water. Always think about the one you're comfortable with, and the opposite transition has to be the opposite energy process. An endothermic reaction always feels cold to your hand. If you stir in some sort of chemical and it dissolves and the beaker feels warmer, that's an exothermic process. If you stir in something and the beaker feels colder, that's an endothermic process. It's actually absorbing heat from your hand in order to feel cold to your hand. So enthalpy is what we're talking about with that endothermic and exothermic stuff. Enthalpy gets the sign of H, and we talk quite a bit about H changing. So we will talk about delta H, the enthalpy transfer between two states. This is a constant pressure system. When we're talking about delta H, the formula for delta H is always the enthalpy of the products minus the enthalpy of the reactants. So you sum the products together if there are more than one product, and you sum the enthalpy of the reactants together if there's more than one reactant. Yep, it's got to be at constant pressure. That matters for some stuff we'll talk about later. Here's a reaction. CH4 plus O2 yields CO2 plus H2O. It's a combustion reaction, actually. Here's the reactant enthalpy. Here's the product enthalpy. In order for you to go from a higher shelf to a lower shelf, energy must exit the system. This is an exothermic reaction because the enthalpy of the products is on a lower shelf than the enthalpy of the reactants. Heat is given off. It's exothermic. Delta H is negative. Conversely, if energy has to go in because the reactants are at a lower shelf than the products, delta H of the products is greater, therefore delta H is a positive value. Heat must go in. It's endothermic. Today is mostly about getting these definitions organized in our heads. Product down here, reactant up there, you must put energy in. Delta H has to be endothermic. If delta H is positive, it's also going to mean that Q is positive. Remember, what's the difference in these? This is enthalpy, and this is heat. It absorbs heat energy from the surroundings, wherever it's at. Endothermic overall. Yeah. You can put actual numerical values to this and say there are 90.7 kilojoules absorbed for every 1 mole of HGOS that decomposes to form this at constant pressure. Constant pressure is unfortunately important. There's the equation as you would write it. Because it's endothermic, you can write energy, or you can think of energy as being a reactant in that reaction. All endothermics have energy as a reactant. Okay, here's another one. Our reactants are higher than our products. That's a P. So you must go down in enthalpy. Energy must be coming out in order for that reaction to happen. Delta H is negative. Q is negative. Your heat is negative. Your enthalpy is negative. The system gives off heat energy. It's an exothermic reaction. The actual numerical value is here. So you've got 2H2 plus O2 yields energy plus 2H2O because this thing is exothermic. Yeah? Just getting the definition straight today. That's all I got to say for you for now. Goodbye.